Hi there, everyone. So, as promised, I was going to record some video content to walk us through the problems from the exam review set which students most requested. So, you'll notice I'm sitting in my Moodle site right now. So, let's take a look and see exactly what the most popular responses on the review survey were. You'll notice not a lot of people replied, so I'm going from a relatively limited data set. We'll see how this goes. So, taking a look at the analysis here, we'll scroll my way down. All right, so it looks like the four most popular answers are the only four that got requested more than once. So it looks like problem 5 got asked for by two people, same for problem 10, same for problem 20, and then problem 15 is kind of the runaway winner. All but one of the responses requested a look at this particular problem. Okay, so I'll go through these more or less in order. We'll start with problem 5. So I'm taking for granted you've got the review problems open in front of you so you can take a look at this. We are asked to find the critical numbers of a particular function accurate to 4 decimal places with the assistance of our calculator friend. So let's do that. Now that we've got the numbers, I'm going to hide the background there just so it's not distracting us with that bar graph. So all right. So as far as it goes here, let's turn on my friend the calculator and let's take a look at what's going on here. I'll center him up if I can. Let me see here. It's not letting me move him. Oh well. All right. Let's see. Okay. Yep. All right. We're just gonna have to go with it as it is because I can't make him move. Anyway, so the function we were given was 2x to the fourth minus 5e to the x, and we want its critical numbers. All right, hopefully you remember critical numbers require us to track down where our derivative is either 0 or our derivative is undefined while the original function is defined. So that means we need a derivative of this thing. So it's not terribly tricky to come up with a derivative in this instance. I'm just going to type it in as I go. So we've got 2x to the fourth. Our buddy the power rule says the derivative there would be 8x cubed. Then we have minus 5e to the x. No fancy, derivative techniques needed. The exponential function's derivative is in fact the exponential function again. So that's the guy we got there. All right. So now, you might be wondering, where does the calculator part come into this? So normally when we've done with one of these problems, we just set the thing equal to 0 and just get to work on trying to get x by itself. That doesn't really work here. Don't try that. That way lies madness. So what we're going to do instead is let our calculator do the heavy lifting for us. So you'll notice I've hit the graph button to take a look at this guy. So it looks like critical numbers, happen where the derivative is 0. That means in terms of the graph, we want to know where this crosses the axis. That happens right here. It happens right here. So we can track those down precisely, as hopefully you recall, using our friend the 0 command in the calc menu. So going into the calc menu, second function of the trace, I want entry number 2. So all right, so I'm going to track down this one on the left first. So my left bound 0 works fine. If you don't want to trace, you could just type these in directly, but it's not too hard to get on the other side of the axis there. So there's my right bound. If we've played our cards right, it only crosses once. We hit enter again to get our guess. All right, so here is our first 0 value. So that's our first critical number. Accurate to 4 decimals, that looks like it would be 1.3336. Okay. Now, we got to go find the second one. Now, the problem is you can see how steep this graph is. It almost looks like a vertical asymptote. I promise it's not, but anyway. So it looks like that's 1, 2, 3, 4. Looks like we're between like 5 and 7. So rather than trying to trace to the right spot on the graph, I'm just going to go in and I'll do the 0 command again. But instead of trying to type in, or trace my way to the number, I'm just going to type in x equals 5. I hit enter. You'll notice that's on one side. My right bound, I'll do 7. Yeah, looks like we're going to catch the crossing right there. So sure, that's fine as a guess. We hit that guy. All right, and that gives us 5.6818 accurate to 4 decimals. So sweet. There's our critical numbers. I promise that's actually all of them for this particular function. So you might get worried that you need to zoom the graph out more, but no, that really is just those two. All right, so problem 10 asks us to evaluate a definite integral, and we'll do that analytically in just a moment, but while I'm here in front of the calculator instead of the whiteboard, I'll show you how we could set this thing up. So let's go back into our function, editor. I will clear out this guy right here. The function we're asked to deal with is the absolute value of 2x plus 7. So, oops, So to get the absolute value, if you don't remember, we go into our math feature here. ABS is living in that number menu. It's number 1. So let's see, and then we have 2x plus 7. All right, so there we go, absolute value of 2x plus 7. And we're interested in the value of this function's definite integral from -6 to 1. So let's go adjust our graph window and play around with that. So we have -6, we have 1. 1 is fine there. As far as a y min goes, I'll do negative, like 0.5. 0 is fine. This thing's an absolute value. It's never going to drop below the axis. Let's see, and up above, the biggest this thing is going to get if we tried plugging in -6, that takes me up to, what, 12. So it looks like about 5. So let's do 5. And yeah, y scale of 1 is fine. All right, let's take a look at our graph and see how this looks. Boing. Oops. Oh, I kind of missed. I forgot. So since we're going past 1, we're actually a little bit bigger here. I'm going to go adjust my window again. Let's change that to like, I think 9 will do the job. So yeah, there we go. All right, so we'll work this out analytically in another video, but real quick, I wanted to take a look at this and remind you, 1, how the calculator does this, and 2, pointing out that connection that we've discussed before as far as linking definite integrals up with areas. Remember, the definite integral is the area between our graph and the x-axis. So we basically want this triangle shape right here, this triangle shape right here. It's easy enough to work out where that break point is and then measure out the areas because these look pretty clearly like triangles, right? But as a reminder, if you were needing to work one of these things out just numerically, in the calc menu, entry number 7 right here is a definite integral calculator. So I hit that guy, and he asks for lower and upper limits. I'll do from -6 up to 1 for my upper limit. I hit enter. There's no need for a guess or anything. It does some fancy shading to tell us what area it's measuring, and then the result is sitting down there at the bottom. So this is actually a good time to point out, funnily enough, this answer, as we'll see when we work this out analytically, should be precisely 26.5. I find it kind of interesting in terms of the way the calculator is doing its like approximate integration or whatever's going on behind the scenes, that it gave us 26.5 and then some extra stuff. So how would we have gotten the 26.5 precisely? We'll take a look at that on the whiteboard in another video, so stay tuned.